Like, no, just explain you could if you wanted to. You could sit there and get your, be an artist. You know, what's graph that's concave up look like with F? Concave up means F's doing something like that, right? And concave down means the graph's what? So you really can improve this sloppy straight line graph I made, true? Like right here, do you agree the graph went concave down, then it went concave up? So what would that look like? Concave down would mean like, maybe the graph went what? Concave down, and then it changed to concave up. I'm trying to talk about what's going on like right there. Let me move it over. Like right here, if you really want to know, it's like some graph went concave down and then concave up. Well, and this is what concave down means for F. This is what concave up means for F. So let me do that again. It's almost like the graph did what? It was like, oh, right here, it was like,
Concave down.
yeah. And then it had a slope of 0, and then it changed to what? Concave up. Right there. Still increasing, but it went, F went concave down and concave up. Point of inflection right in the middle. See? So I've seen students build clear just a pretty graph, you know, if you want to. Then they're like, can I get bonus for this? I got a really nice graph going on here. They really showed this whole design going through. I'm okay with that? Alright, that's some abstract stuff, but not cool.
Can you
Not
do?
bad at all.
Could you do one more if that's cool?
Yeah, let's do another one now.
Yeah.
How about you all make it up? Does that work? Amber, you want to come draw it? Just put part on top, part on the bottom. Hey, you want another one of these, right? Alright, you're going to make it. Do whatever you want. I don't care where you do it. Make it smooth too. Make it like a polynomial. And then, while she's making it, I'll go over here, find another eraser. Thanks, Amber. And I'll erase all these answers. I'll grab this. This will be fun. And we don't care if it's really simple. Do whatever you want. Do whatever you want. Make that thing smooth. I like it. Yeah! Holy cow. I love it. Perfect. That was great. I'll make up x values. I'll just put some x values. I do want to point out this graph right here is f prime. So listen, and when this is f prime. Right there. Amber, that was great.
Thank you.
All right, let's see. What's that x value? Hey, I'm gonna let this thing just swing up forever. All right, that's x equal to -8, -6, -4, -3, -2, -1. That's 0. Not drawing a scale though. Don't worry. Will that work? So -1, -2 right there, -3, -4, -6, -8, and when that's 1, that's 2, that's 4, that's 6, and that thing takes off. See, here you go. You might go, wait, that kind of bottomed out at 3.8 or 3.9. Oh, we'll just say 4. Right there. Take your time, everyone. I know you got a lot of writing to do. You got to put all that down. We're going to find all x values which f contains a relative or local mass and a local min. And where's f increasing? Where's f decreasing? Find all x values which contains a point of inflection. Where's up concave up? I make this problem worth like 7 points on a test. My reasoning, I mean, I could have made it more than 10. I've seen some students, they love all of chapter 4. Some students, and they hate this. I mean, they love the optimization at the end. They love the application of Newton's method, which we're going to do later this week. They just don't like this. So that way, you know, some of you are like, all right, I hate this. They get their, you know, they can still score very well. Hey, remember the game, above or below. If it's above, the graph's what?
Increasing.
So I'm already looking. Where's it above?
-4 to now, -2.
All the way to the -8? -4 to -2, I love it. Anywhere else?
0 to 2,
There you go. This is when F's increasing.
6 to infinity.
And I almost missed the end. I got so tired of when I was like, I must have hit them all. But Amber made a tough graph. It was good. Challenge. So F is decreasing when, what, -8 to -4? And from -2 to 0? And 2 to 6? Alright, where are the maxes and mins? If you want to use this, you can. I don't know, hey Kayla, do you like these kind of things? I mean, some people like that.
I don't like that.
See, she doesn't. I kind of agree with it. It's more conceptual. They just memorize it. They just go, all right, whenever the graph went like that on the x-axis, right, across from the top, because that means the graph what? Conceptual is, it was increasing and then it was decreasing. This thing was going up, then it was going down. There it is. There's a relative max. There's another relative max. There's another relative max. Here, here, and there.
Oh, so relative max is basically if the graph is like this way you can count.
You bet, Art, I love it. And you know why? Here's you and I conceptual. We're like, yeah, because that means we describe graphs left to right, and we're always saying, all right, the graph was increasing and then decreasing.
Decreasing, okay.
It's a relative max. That's why. That's what's going on here on conceptually. We're saying the graph was increasing and then it was decreasing. It's got to be a relative max at those locations.
You drew a second graph for the other question. Could you do the same one for this? Like,
Oh, yeah, you want to try it? No, let's be sloppy, okay? Hey, let's just be sloppy. We'll just do straight lines, right? Let's talk about it. So remember, anything above means the graph was what? Going up. When anything below, the graph was what? Going down. All right, here we go. And you go, where do I start? I can start anywhere. I can just start right here because I want to have enough room. Right? All right, look, it's above. From here to here is above. So that means the graph did what? F went like this. F went up. Kind of sloppy, but now stop. Right there, stop. Now what did the graph do from here to here?
1 down.
Went down. Stop. I know it's sloppy, straight lines, but it's the idea. What did it do from here to here?
1 up.
Went up. Stop. Right there, it stops. It's going to go what?
Down.
Down. It looks like it'll go way further down. You can compare areas.
Mm-hmm.
If there's more area underneath, that means it went further down. I mean, that's the idea. But hey, I'm just go down like this. Stop, then what? Go up. Then what?
Go
From there to
down.
there, what?
So
Went down, stop. Sorry, I'm running into the other graph. And then what would it do?
Go up.
Go up. And you can look at that thing and you go, when was it increasing, when was it decreasing? And you'll see everything lines up. Then you can go back in and improve it with nice curves if you wanted to. Only if you wanted to. Alright, we're all at maxes.
But we can do it from the first derivative. Like if it is over the axis, then that's increasing and
That's right.
yeah.
Then you can go back in and make it nice where it's concave up and concave down.
But for lazy people like us, we don't have to.
I know. I decided, it can frustrate you when someone said, hey, graph this thing. Now you're trying to do, you go back, you start trying to really fancy it up with this stuff, right? Ooh, when was it concave up or concave down? And changing it, points of inflection.
So the only time you have to draw the first graph with the straight lines is if you wanted to see when it was increasing or decreasing.
That's right, and you don't have to.
You don't have to.
You don't have to.
When it's a positive.
I've got, for years, great question. I've graded these for years, and I've seen no work.
Okay.
I've seen no work from a student. And they have just gone,
Yeah,
bing, 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 bing,
that
bing,
makes
bing.
more sense to me than the.
And they're just sitting there going, oh, I got it. And they're just answering everything. So very good. Hey, so where's all the maxes? -8, -2, and there's one more, where?
0, 2, positive.
+2. So where's all the mins? -4, 0, an x equal to 6. If you want to put an x in front, you can. Here, an x equal. Just list the numbers. I want to make it easy for you so you can just list these numbers in. -8, -2, 2, -4, 0, and 6. All right, now points of inflection. Do you remember where to look?
Yeah, at the
And
slope.
The hills, the humps. Look for the humps, right? There's one. Point of F. Point of F. I'm gonna write of F so someone didn't think I'm doing point of inflection of an F prime. I'm talking about the actual point of inflection of the original F graph. Poi, 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 poi. So there's a bunch. Boy, this graph is changing concavity all over the place, isn't it? But hey, she made a graph that's kind of like a sine, like a trig function. You got it at what, -6, -3, where else? -6, -3,
-1,
-1,
+1,
+1,
4.
and then 4. Thanks for your great graph. Now when we gotta talk about concave up, this is the last thing. And then concave down. Where do we look? Well, this is F prime graph. This concavity stuff, everyone? F double prime tells us about it. A graph is a function is concave up when its second derivative is positive, right? Here, F is concave up. Second derivative positive. A function is concave down. Oh, second derivative is what? So I like to circle. You ready? I'm gonna circle.
Or also, don't you have to look at between two POIs?
Yeah, it goes between poise. I love it, just between two POIs. So look, from here to here, concave up.
Up.
And then from here to here,
Concave up.
concave up. I like the actual circle, so you can distinguish this from all my other writing.
And
Then again, from what?
4 to infinity, concave up.
Concave up. The opposite would be concave down. Has to be between the poise. Like he said, between the POIs. Or if you call them IPs. So here we go. From -6 to what? -3. Union. What was that? -1 to
1
-1 to 1.
and 4 to infinity.
4 to infinity. Then concave down. Okay, -infinity all the way to that -6. Union. -3 to -1. Union.
1 to 4.
1 to 4. You're next. I'm trying to think of the craziest thing ever. Josephine, I could actually in here draw a straight line like that. But do you remember when there's a point like this? No JVCs, no corners or cups. So the derivative of that would be non-existent. Does that make sense? So I won't do that. Hey, did anybody have any other questions about problems from here? When we did first derivative, second derivative, concave up, concave down? where you gotta answer is when there's a function given. Does everyone get that? Awesome. Don't worry, everyone. I didn't want you to think like, oh, he's not gonna do any more of those. We're gonna get into 4.4 now. But sections 4.5 and 4.6, we don't have to do all the problems, but it's just another section that just go, okay. Can you put it all together now? You go, really? Yeah. Can you still again find where a function's concave up or concave down or where it's increase or decrease? And in those problems, Amber, they give you a formula. Okay, everyone, they give you formulas there. But let's now have some fun. Everyone, 4.4. What are we returning to? Limits. This is a cool rule. Now, if you go to 4.4, you all see a strange word at the top? Just look at the name.
L'Hopital,
L'Hopital.
Law Hospital.
Yeah? I'm gonna write it down. Seen it spelled a couple ways. It looks like a hospital. Everyone, this is for indeterminate form. Do you remember us talking about that before? Indeterminate form. What's one indeterminate form?
0 over 0,